Friends, these days lots of social scientists, PhD students, young faculty members in several disciplines, social sciences, management, organization behavior, are using structural equation modeling. And this presentation focuses on that. This is based on my informal interaction with PhD students and young faculty members at several institutes. And what I noticed that although they know how to apply SEM, they can use SPSS or other packages or R very well to apply SEM and arrive at inferences. But there are lots of conceptual misunderstandings about the technique. So I thought that in this presentation, I will focus mainly on conceptual aspects, and I will avoid showing application of AMOS or SEM in general to data. I will also avoid mathematical aspects of structural equation modeling. I will just focus on concepts. What is this? What is SEM? What does it achieve? What are its limitations? What is its relationship with regression analysis, logistic analysis, correlational analysis, path analysis, and so on? And what are the limitations of SEM? I think that many students and young faculty members will find this discussion interesting. So I have made a presentation, and I would like to share my slides on that. Friends, the title of this presentation is Correlation, Regression, Path Analysis, and SEM. Actually, I will say that SEM is only an advanced version of correlational technique. To be clear about SEM, you have to be clear about as simple a thing as correlation coefficient. Now, correlation coefficient between two variables x and y shows the strength of relationship between them. That's all. And under certain conditions, that the relationship is linear and all that. I suppose you understand the meaning of linearity. But in the real life or in the real world of data, we deal not with two variables, but a large number of variables. And sometimes with groups of variables or abstract variables, latent variables, factors, which are affected or which affect a number of measurements or items or variables on which data have been collected, such as beliefs, attitudes, comprehensive knowledge of HIV, and so on. And directionality. In correlation, there is no direction. It's simply the strength of relationship. When you are able to show that one of them, like X, is an explanatory variable or independent variable, and Y is dependent variable, or Y is the focus of your study, you are explaining variations in Y in terms of X, then you are using the law of relationship or binary regression analysis. Normally, we assume that both Y and X are quantitative variables, and there are no measurement errors, particularly in X, and that X is the real cause of Y. No other factor is involved in explaining Y. If these assumptions do not meet, if the relationship is not linear, or if X has measurement errors, or there is endogeneity or reciprocity of relationship or simultaneity of relationship, then bivariate regression would not work. But that's a separate issue. Actually, you will see that gradually, as we keep on dropping the assumptions of correlation coefficient, we move towards structural equation modeling, which is the most general model for analyzing relationships between variables and abstract factors with or without reciprocity, with or without measurement errors. And it combines both individual items or variables and also groupings of variables called constructs. Now, sometimes you have several explanatory variables, means in place of x in bivariate regression, you have k variables as explanatory variables, x1, x2, xk, and you are dealing with this equation y equal to b0 plus b1 x1 plus b2 x2 plus dot 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 bk xk plus e. E is an error term which stands for measurement error and also for effects of those factors which have not been included in the model but which might affect y. This is multiple regression analysis. Again, there are so many assumptions under which regression analysis works. Relationships are linear, they are recursive, means only x's affect y does not affect x, y is the dependent variable, x1, x2, xk are independent variables, and all the independent variables are uncorrelated. Means correlation coefficient between x1 and x2 is 0, x2 and xk is 0, like that. All the correlations between pairs of explanatory variables are 0. There is no measurement error, no endogeneity, means there is no specification error, there is no z which affects y, and also one or more of explanatory variables x1, x2, xk, which has been ignored in the analysis. Only under these assumptions we say that the partial regression coefficient b1, b2, b3, bk are blue, means best linear unbiased estimates. I know that you understand the meaning of blue. I could talk about these things in more detail, but my purpose today is to focus on SEM. These can be compared if variables are standardized, because we know that these are affected by standard deviations of explanatory variables. So, if the standard deviations are not same, these cannot be compared. This is the conceptual model. Actually, I always motivate students to show their conceptual model in the form of a diagram. That makes your analysis plan easier, that makes your understanding clear, that makes you take a decision regarding if some explanatory variables have been ignored or not included in the model, which are crucial, and also draw your attention towards the nature of relationships between explanatory variables and the dependent variable. Here is the conceptual scheme of multiple regression analysis. Y is the dependent variable, x1, x2, xk are independent variables, all of them affect y directly, and the relationships between x1, x2, x3, xk on the one hand and y on the other need not be of the same quantum. So, for example, x1 has a correlation of 0.78 and positive, while x3 has a correlation of only 0.22 and is negative. So, correlations may differ, and ultimate purpose of applying this regression analysis is to identify which factors are more crucial in explaining variations in y, which is the focus of our study. Now, friends, sometimes we have dummy variables because there are some x's or in some cases even y, which cannot be measured in terms of an interval scale or ratio scale. For example, one of the independent variables may be sex or gender, and in that case you can use a dummy variable, one single dummy variable, assign value of 1 to that dummy for females and 0 for males, and run your usual regression analysis. The regression coefficient of gender will then tell you what is the mean difference in Y between females and males, keeping all other explanatory variables fixed. Sometimes you have 3 or more categories, like in the previous example, if gender is divided into 3 categories, males, females, and others, then you will need 2 dummies. Actually, as a rule, if you have a qualitative variable with n categories, then you will need n minus 1 dummy variables. And the meanings of regression coefficients will be the differences in the mean values of the dependent variable between a particular category and the reference category. Remember that make an extreme category the reference category. Like, I would prefer that if your qualitative variable is gender, then make others the reference category, or you can make males the reference category. If you are dealing with a caste, make scheduled caste as the reference category, or the other caste as the reference category. Extremes should be made the reference category. If the dependent variable is categorical, then you can still apply multiple regression analysis, provided the probabilities are expected to be between 0.20 and 0.80. Suppose your dependent variable is migrant, non-migrants. You want to explain the migration status in terms of a number of socioeconomic variables, and the chance that a person would be a migrant lies between 0.20 and 0.80. It is not less than 0.0, it is not more than 0.80. You can apply multiple regression. Otherwise, you can apply discriminant analysis. Or if the dependent variable is divided into more categories, say 3 categories, and the dependent variable is measured on ordinal scale, then we go for ordinal logistic or multiple logistic. So sometimes it's not just dependent variable is divided into 2 categories, say those who suffer from poverty and those who are above the poverty line. It can be something, it can consist of 3 or more categories, like anemia, mild anemia, moderate anemia, severe anemia, or maybe a category of no anemia. Then you will require applying multiple logistic. Okay. Now, what takes us towards SEM gradually is the situation in which our independent variables are actually not independent. They are correlated. If they are correlated, then the first technique that comes to our mind, and which will work well in certain circumstances, is the path analysis. Path analysis is superior to multiple regression analysis when some of the predictors or all of the predictors are correlated, and that can be known by computing VIF or square root of VIF, which tells us by what amount standard errors of different explanatory variables are inflated because of multicollinearity. But the relationships are recursive. Usually path analysis is used when the relationships are recursive, although there are path analytic models for non-recursive relationships also. And in case of multicollinearity or a network of relationships among independent variables, then you can calculate direct effect of a variable on the dependent variable, indirect effect through other variables, joint effect of two variables, and net effect of a variable. But here again, in path analysis, there is no construct or there is no grouping of variables. All the variables have been measured in the survey, means direct data on all the items, all the measures, all the variables that have been included in the path analysis have been collected. No issue. Actually, path analysis can be seen as a technique of multiple regression only with the standardized variables, provided the relationships are recursive and it is possible for us to make a diagram in which for understanding relationships we can move from one direction to another. All the relationships are either from left to right or from right to left. Okay. This is the conceptual diagram of path analysis. Here there is measurement 6, which is something in which we are interested. This is the focus of the study, and this is explained in terms of other measurements or other variables, measurement 1, 2, 3, 4, and 5. Relationships are recursive. You move from left to right, but there are correlations between different explanatory variables. Like if you take measurement 3, then measurement 3 has a direct effect on measurement 6, and measurement 3 also has an indirect effect on measurement 6, which is through measurement 4. The correlation between 3 and 4 is minus 0.05, and between 4 and 6 it is minus 0.34. Direct correlation is 0.71. Similarly, when you move from measurement 2 to measurement 6, you find that there is a direct relationship, and the correlation of measurement 2 with 6 is minus 0.54. There is indirect relationship through measurement 5, and the correlations are minus 0.18 and plus 0.89. Now here you can calculate what is the effect of measurement 3 on 6, measurement 2 on 6, measurement 2 on 5, measurement 1 on 2. All the variables which are influenced by other variables are called endogenous variables, and those variables which do not have a cause, which only have effects, they are called exogenous variables in the system. No variable as such is endogenous or exogenous. It depends on your conceptual framework. Actually, I give lot of importance to review of literature and developing a conceptual framework prior to going for the field work or analysis of data. Review of literature will tell you what are your endogenous variables, what are your exogenous variables, which variables might contain error, like measurement 3 contains an error E. Measurement 6 also contains an error E. It is possible for, in path analysis, it is possible for us to understand the effect of errors also. Now friends, gradually as we move from path analysis to structural equation modeling, there is something called principal component analysis. Now, principal component analysis is the gateway of structure equation modeling, also called simultaneous equation modeling. Now, what is achieved in principal component analysis is that we try to form groups of variables which are mostly interconnected, and in this conceptual framework, I have tried to show through linkages that this principal component 1 is a component or a factor which depends on all the measurements. There are 6 measurements, and principal component 1 is a linear combination of all these 6 measurements. Friends, principal component 2 is also a linear combination of all these 6 components. Principal component 6 is also a linear combination of all the measurements 1 to 6. I have shown relationships of PC1 and PC6 to all the measurements. I have not shown relationships of PC2, PC3, PC4, PC5 with all the measurements, because I thought that the graph or diagram would become clumsy. But the fact is that all the principal components depend on all the variables. But what we find interesting in this principal component analysis is that there are some principal components or some factors, although all the factors are linear combinations of them, but it is possible to derive certain principal components which explain a large part of the total variation in the data. Like PC1, let me repeat that all the PCs are linear combinations of all the items, but PC1 is such, or it has been obtained in such a manner by using such a technique that it explains almost 38% of the variation of the whole data. Then comes PC2, which explains 20%. PC3 explains 18%. PC4, 14. PC5, 6. And PC6 explains only 4%. If this is the situation, one can as well decide that in place of working with 6 variables, he would like to work, or she would like to work with only first 2 components or first 3 components or first 4 components, depending on how much variation they want to cover, how much variation in the data they want to cover. So all the measurements are linearly related with all the PCs. You can express any measurement as a linear combination of all the PCs. You can also express any PC as a linear combination of all the measurements. So, and because of this reciprocity kind of relationship, in some conceptual frameworks of factor analysis, we do not show the relationships through arrows, because arrows show the direction of relationship. We simply make straight lines, because PC depend on measurements, measurements depend on PCs. So simply relationship. So friends, when it is possible for us to identify a few principal components for further analysis, which explain or which contain a large part of the data. You see, there is a graph on the left hand side of this screen which shows that as factors are shown on x-axis, F1, F2, F3, F4, F5, and what percentage of variation they explain is shown on the y-axis. This is also called eigenvalue of the factor. So first factor or first principal component explains the maximum, then second, then third. And you can see that after considering 2 or 3 or 4, depending on the data, then further addition to variation explained by applying factor analysis or principal component is not much. So we stop there, and we will say that all the variables will be reduced to these many factors only. Now here was an example of 6 measurements and 6 components. But some factor analysis or principal component analysis is useful when number of measurements is very large. It may be 40, 50 or even 100. And if you can reduce the variability in the data in terms of 3, 4, 5 or 6, even 6 or 7 principal components and or factors, you have achieved, you have gained in theoretical terms that now you do not have to work with 100 variables, you can as well work with 6 factors. Friends, now you may ask, what is the difference between principal component analysis and factor analysis? If these are two different terms, then there must be some difference. And the difference is that in principal component analysis, we have as many components as the number of variables. But in factor analysis, we consider only a few factors which can be decided by us, or which can be determined on the basis of the script plot shown on the left hand side of the screen, or there can be other techniques, like somebody can say that I will consider all the factors or all the principal components which have an eigenvalue of more than 1 and ignore all other variables with eigenvalue of less than 1. What does factor analysis give? So if and this is an important distinction, that now a factor is a linear combination of all the measurements plus an error term. There is no error term in principal component analysis, but there is an error term or uncertainty in factor analysis because you have not considered all the factors. And a factor is certainly a linear combination of all the variables plus an error term. Gradually, when you have actually developed the factors and you find that factor 1 is influenced by x1, x2, x3, x4, x5 only, and other variables do not affect the factor very much, then you can confine your expression to a linear relationship between these variables only. So then there is a significance of the error term. So when you write that F1, PC1, principal component 1, is a linear combination of all the variables. But factor 1, which explains the majority of variation in the data set, is a linear combination of a few measurements or few variables only plus an error term. So I will say that F1 is a linear combination of x1, x2, x3, x4, x5 plus error. Factor 2 is a linear combination of x2, x7, x9, x95 plus an error term. That is factor analysis. This is a special case of principal component analysis, summarizes data in terms of a few factors, which may be orthogonal or independent, uncorrelated, or they may be oblique. Sometimes using oblique factors gives better results, a better fit to the data. This factor analysis also gives you commonality of all the variables, that how much variance of a particular variable is shared by the factors that you are considering. If you consider all the factors, means if you consider all the principal components, then the commonality is 100%. But if you are considering only a few factors, 3, 4, 5, 6 factors, then what proportion of variance of x1 is explained by these factors is called commonality. That's an interesting indicator. Then percent variance explained by each factor separately and cumulatively. You can also identify surrogate variables which have the highest correlation with a factor. So later on, you can just replace factors by surrogate variables and say that what the analysis of 100 variables could achieve, Now the analysis of 4 or 5 variables alone can achieve the same. So there is a big gain. It's a data summary technique, but the assumption of linearity remains. And yeah, one advantage of factor analysis is that sometimes you want to develop a scale, a weighted scale based on all the factors or all the variables on which data have been collected. Suppose I want to develop a scale of progress in health in a particular state of India, then progress of health is measured in terms of a number of variables. Decline in infant mortality, decline in neonatal mortality, decline in maternal mortality, decline in overall death rate, improvement in life expectancy, improvement in number of nurses per thousand population, or improvement in number of doctors per thousand population, or number of health facilities created, or number of mental health facilities added, etc. Now, if I run factor analysis, the advantage would be that my first factor, which will depend, or my first principal component, which will depend on all of them, can be taken as an overall index of improvement in the health system. It covers all the indicators, all the variables, infant mortality, maternal mortality, everything has been covered, nurses, doctors, everything has been covered. All indicators of health that you can imagine, including inequalities, disparities, urban, rural, caste, and so on. Everything can be considered as a variable. And this health index as principal component 1 or factor 1 gives you a linear combination of all of them, but weights have been determined by application of factor analysis. This is the best scale one can think of. So if you are ever thinking of constructing a scale based on the number of variables, you can apply factor analysis, and the first principal component or the first factor can be taken to be the weighted linear estimate of that weighted score. But remember, here is a catch, that fact, unlike other types of analysis, graph, charts, univariate analysis, t-test, f-test, application of factor analysis doesn't always make sense. It adds to analysis only if within different factors or within different principal components, there are clusters of variables which make an overall sense. So it is said that after running the factor analysis, you show the results to experts, 5 experts, 10 experts, and ask them to name these factors. If they are able to make sense of these factors on the basis of on which variables they depend, then only your factor analysis is successful and you can name the factors. Otherwise not. These factors are called constructs because they are certainly measuring some aspect of the problem, but they are not directly measured. What is directly measured is called item, and the cluster of items in terms of which data get reduced is called constructs. Now, these constructs may be used like variables as dependent variables or independent variables or both in a more complex system of relationships or equations. They may be called formative and reflective. Sometimes students have a confusion regarding what is a formative factor, what is a reflective factor, formative construct, reflective construct. Friend, there is no variable or no factor as such is formative or reflective. It depends on your use of that construct. If that construct depends on a number of items or measurements or variables on which direct data have been collected, you are dealing with formative. And if if you are trying to explain some variables directly observable in terms of these constructs, then you are treating that construct as reflective. Like socioeconomic status. Socioeconomic status on the face of it is a formative construct because it depends on income, occupation, years of schooling, etc., etc. But it can also be used as a reflective construct if you are going for understanding the relationship between socioeconomic status score and say knowledge of HIV, risk behavior, use of family planning methods, and so on. So it depends on the use. In as we move towards structural equation modeling, which means considering all kinds of relationships between variables and between factors, and recursive and non-recursive, means simultaneous equations, unidirectional relations, and numeric variables and categorical variables, ordinal variables, a hodgepodge of all kinds of things. And we keep on dropping assumptions of multiple linear analysis. Then you see in the model, there are some constructs which depend on the items and may contain errors. They are called endogenous. There are others which affect the other items or the other constructs. They are called exogenous, as endogenous and exogenous variables in the path analysis. Path analysis contains only variables, while this structural equation modeling considers both variables as well as factors or constructs. Exogenous constructs do not contain error. This is the conceptual framework of structural equation modeling. So there are measurements. Data have been collected on measurement 1, 2, 3, 4, 5, 6, 7, 7 and 8 shown on the right hand side. So there are 8 variables on which data have been collected. And there are, 9. There are 9 variables on which data are collected. Measurement 1, 2, 3, 4, 5, 6 shown on the left hand side, and 7, 8 and 9 shown on the right hand side. Now all these measurements contain error. Measurements are usually shown, measures as well as errors are shown in terms of squares, while factors which are abstract and on which direct data have not been collected, but they are very important conceptual categories of analysis for us. They are called constructs, and they are exogenous and endogenous. In this model, there are two endogenous latent variables, 1 and 2. They are shown in terms of ellipse. You can show them in terms of ellipse, or you can also show them in terms of circles. There is one exogenous latent variable. The term latent variable or construct or factor or component, they are often used interchangeably. So there are 2 endogenous latent variables or constructs. First one depends on measurement 1, 2 and 3. Measurements are variables, actual variables on which data have been collected. Endogenous latent variable 2, or means construct 2, which is endogenous, depends on 4, 5 and 6. This exogenous latent variable 1, this influences endogenous variable 1, means one factor affects the other factor, one construct affects the other factor. This also affects the other construct or endogenous latent variable V2, and this affects measurement 7, measurement 8 and measurement 9. This is the nature of path simultaneous equation model. all the arrows show the path of relationships in which we are interested. So a path diagram of relationships in structural equation modeling is very general. It contains variables, it contains constructs. Constructs are basically linear combinations of variables only, but they appear as though they act as variables. That is why endogenous latent variable v1, this is a construct, but we write endogenous latent variable 1, which depends on 1, 2, and 3 variables on which data have been collected. So this is a conceptual framework, and you can also see that measurements and these constructs may be affected by an error term also. Endogenous variables, endogenous constructs are affected by error term. Exogenous construct or exogenous latent variable is not affected by any error term. So when is structural equation modeling used? To test a model consisting of measurements, direct variables. Your survey may include, say, 100 variables, so all 100 variables are included. Latent variables or constructs, which are linear combinations of these variables, but which measure something interesting about the data, and they are abstract. Like you may have data on time use, but the concept of modernity in terms of time use data, this modernity becomes a construct. You have not directly collected data on modernity, you have collected data on time use. Sometimes constructs depend on variety of variables. So your modernity as a construct may depend on your orientation for time. It may also depend on efficacy. It may depend on the need for achievement, or it may depend on many other social variables, psychological variables, political variables, or cultural variables, and so on. So there are variables, there are constructs, latent variables or constructs. There are errors. There are relationships between measurements and latent variables. And these relationships may be recursive or they may be non-recursive. And so this way we have a structure or a structural equation model. Now, some questions which students often ask: what is an acceptable sample size for applying structural equation modeling? I would say not less than 100. Some books would show a figure ranging from 10 to 20, that the sample size should be 10 to 20 times the number of parameters to be estimated. Parameters are the coefficients of correlations in which you are interested. They may be correlations between variables, or they may be between factors, or between factors and variables. Because you see, when data are collected on the basis of sampling, then no matter what you estimate mean or mode or median, or you estimate regression coefficient or path coefficient or variance covariances, everything is subject to sampling fluctuations. And to minimize sampling fluctuations, one of the ways is to increase the sample size. That's why I say not less than 100 or 10 to 20 times more than the number of parameters to be estimated. Now, friends, oftentimes a distinction is made between exploratory factor analysis and confirmatory. Exploratory factors are a limited number of factors. Actually, what I mentioned a few minutes before, talking about principal component of factor analysis, that was called exploratory factor analysis. That is exploratory. We explore if there are factors, meaningful factors in terms of which large data can be summarized. Confirmatory factor analysis uh, provide the test of validity of a model containing measurements and factors. So, on the basis of review of literature, we may develop an understanding, a conceptual understanding of major relationships between measurements and factors, and we want to test whether that understanding is okay and that we want to do on the basis of data. So, we go for confirmatory factor analysis. Remember, I have very commonly seen in PhD thesis that students have used exploratory and confirmatory factor analysis to the same data. This should not be done. Both of them should not be applied to the same data. If you have already collected data and you are applying these two techniques, what you can do is that you divide data into two parts. Use the first part for exploratory factor analysis and the second part for confirmatory factor analysis. Now, in SEM, how would you assess whether the model of recursive, non-recursive relationships between factors and measurements or variables is validated by the data? So, as in multiple regression analysis, all of you know that in multiple regression analysis, capital R square is the test of goodness of fit of the model. We need something in SEM for the same, to achieve the same purpose. And interestingly, you find, imagine that you have the original variance covariance matrix between all the variables included in the model. Okay, let us call it S. S is the variance covariance matrix. If variance covariance matrix is estimated on the basis of standardized variables, then it becomes correlation matrix. So, SEM can be run on variance covariance matrices or on correlations, no issues. After you have hypothesized a pattern of relationships between measurements and factors, you do that, estimate the parameters, means coefficients of correlations, and then again by using that model, calculate a new variance, covariance or correlation matrix. Let us call it sigma. Then it has been found that S minus sigma follows a chi-square distribution. If they are very close, chi-square will be 0. That means model is good. If they are different, then there is a gap between the original variance covariance matrix and what you get on the basis of the model after estimating the parameters. And that means model is not good. For a long time, let me tell you that for a long time I was confused that S and sigma are matrices, while chi-square is a univariate variable. Yes, books write S minus sigma, but they mean determinant of S minus sigma. Now, determinant will be a univariate thing, a scalar quantity, and that scalar quantity follows a chi-square distribution. But chi-square has some degrees of freedom also. So, yes, in SEM we have degrees of freedom concept. Degrees of freedom of SEM is if number of observations, if number of variables is k, then the degrees of freedom is k multiplied by k plus 1 divided by 2 minus t. We will come to t. Here k, where does this k into k plus 1 by 2 come from? Actually, if there are k variables, you have k into k minus 1 by 2 covariances and k variances. If you add the two, variances and covariances, then you get k into k plus 1 by 2. And T means restrictions or parameters estimated from the model. SEM is an interesting and useful technique, but you have to be very, very careful about use of certain terms like observation. Earlier, the term observation in statistics was used for number of respondents, a number of experiments, a number of subjects, number of groups. But here observation means number of things that you are comparing, and what you are comparing here is variances and covariances. So observations means number of variances and covariances, which is k into k plus 1 by 2. So this is observation, not the number of respondents. Number of respondents is not important here. Remember that chi-square depends on sample size, so there are issues in application of chi-square, and better measures are available. There are two types of better measures. Some are based on the errors in the variance covariance matrix, means how do the original variances and covariances differ from those estimated after fitting the model. It may be negative or positive, but there is a difference. If you summarize those differences in certain terms, like root mean square residual, RMR or RMS, you have another measure of goodness of fit. Then if you have two models, then you can compare differences in chi-squares and adjust them for the differences in degrees of freedom, and you get other measures. So there are three types of measures: simply chi-square, root mean square residuals, and chi-square goodness of index. Three types of measures. There are so many indices in each of these categories, which you will get from the application of SEM. Friends, degrees of freedom is this. If there are p endogenous variables, q exogenous variables, means total number of variables is p plus q, then the degrees of number of observations would be p plus q into p plus q plus 1 divided by 2 minus t. T is the number of parameters to be estimated. There is an interesting way of calculating t, or number of parameters to be estimated in the model. The number of variances and covariances between measured exogenous, independent, or latent variables. Second, the number of path or regression coefficients connecting any two latent variables. Number three, the number of error terms on endogenous, dependent, latent variables. The number of factor loadings for endogenous or dependent measured or latent variables. The number of error terms on endogenous or dependent measured variables. Actually, in very, very simple terms, for the purpose of clarification, for your conceptual understanding, I am telling you in the simplified form that all the arrows that we have shown in the model, confirmatory factor analysis model, or all the path coefficients that we have estimated, they are the constants of the model and observations minus those constants. If I go back to SEM model, conceptual framework, all these things 1 to 5 are shown as arrows, and so observations minus these arrows make the degrees of freedom. Now, students also ask me, can I run confirmatory factor analysis on Excel data? Most people use Excel data, some use SPSS, so obviously I can understand their question. The answer is no. If you use SPSS, you need analysis of moment structure, or called AMOS. You have to buy AMOS separately, or there is another package which is called linear structural relations, LISREL. So either AMOS or LISREL. The ordinary SPSS package that we are using for univariate and multivariate analysis, t-test, z-test, factor analysis, that will not work. AMOS is required. And if you are using SAS, you may use a separate package called CALIS. So you have to buy Amos, Lisrel, or Calis. Now, what are the limitations of SEM? I told you that it may be interesting to apply factor analysis in your research, but factor analysis is risky because application of factor analysis is not always found to be useful or successful unless you can find meaningful constructs as clusters of variables. Your factor analysis is not successful and all your labor is wasted. Structural equation model must also be seen along with its limitations. SEM is a linear. Linearity remains. So if there are non-linear relationships, be careful or do something about them. Transform them to logarithmic scale or do something. Use quadratic equations. But as such, SEM will not give you good results or dependable results if some of the relationships are non-linear. It does not work if there is multicollinearity. Many people think that, okay, we use path analysis when there is multicollinearity, and SEM is only an advanced version of path analysis. So multicollinearity question will not arise. I keep on telling my students or wherever I go that multicollinearity is a serious issue, and application or usefulness of SEM is limited by presence of multicollinearity. Another thing, check whether data are free from outliers. The data should be free of outliers or values which are not representative of the pattern. If they are present in the data, too high, too low values of different variables or factors, then you have problem. Another assumption is that your measurements or your variables which you have actually measured follow a multivariate normal distribution. I can also say that each variable separately also follows a normal distribution. There is over-identification, means observations are more than the number of parameters that you are estimating. Remember, observations, the term observations refers to number of variances and covariances. Then ratio of maximum covariance to minimum covariance should not exceed 10. Yeah, check your variance covariance matrix carefully. If there are some covariances which are too high, some too low, like one is 40, another is 4, then be careful. What you can do, you can still run SEM, but you multiply that variable which has covariance of 4 by 10. So it will also have a higher covariance. You cannot corroborate a model. Remember, in philosophy of social science or philosophy of sciences, we often remember Karl Popper or neo-positivism, according to which we can never corroborate a model. We can only test or we can only attempt to falsify a model. So we can never say that if my chi-square, goodness of fit indices, or root mean square residuals, they suggest that model is fit. I may not reject the model, but it does not mean that the model that I have fitted to the data is the best possible model. Maybe there are other models which will fit equally well or better. So this makes a scientist, a social scientist, modest that you have not discovered the truth. Okay, if the goodness of test measure suggests that your model is okay, you will not reject it, but it does not mean that the model that you have proposed or hypothesized is the best possible model. There are alternative models which will fit equally well or which can even be better than this. Thank you, friends. So I thought that there are some doubts about application of SEM. I have gone through several papers which come to us for editing or for reviews from different journals. I have seen PhD theses. I have seen my own students in HS department and management applying SEM, and quite often the understanding of SEM is not so good. Nobody talks of multicollinearity in SEM. Nobody talks of ratio of maximum and minimum covariances in SEM. Nobody talks of linearity of relationships. You have to examine all these things, and if these problems are there, there is no doubt that as compared to simple correlational analysis, SEM is very advanced because it can take care of all types of variables, numeric, ordinal, or categorical, 2 categories, 5 categories, 10. It can take care of that. It can take care of relationships without direction and with directions. It can take care of reciprocal relationships. It can take care of relationship between constructs or dimensions of the problem on which direct data cannot be collected. You cannot collect direct data on intelligence, but you can give intelligence tests and in terms of a number of items and construction overall IQ score. That IQ score is a factor. Similarly, values are factors. They comprise of several values, several types of evaluations or standards, which vary from culture to culture. Comprehensive knowledge of HIV is not a variable, it's a factor. Okay. So similarly, job satisfaction, it can be seen as a factor. It depends on many things, many types of or satisfaction with respect to many things. Spiritual climate, organization climate, spiritual organization climate, it's a factor. It consists of or it depends on a number of variables: trust, leadership, motivation, reward system, culture, so many things it depends on. So when you are SEM is a good technique when you have to struggle with patterns of relationships between your measurements and factors, and your measurements and factors are uh, they, uh, they are related to each other in variety of ways, directly, indirectly, and sometimes also um, in reciprocal ways. You can apply this, but it does not apply everywhere. And just check what are the limitations of SEM. If if there is a problem of multicollinearity, too much, a small multicollinearity, yes, this is the purpose we have devised SEM. But if there is too much of multicollinearity, that will affect your results. You will not get a good model. Also, remember that exploratory factor analysis and confirmatory factor analysis cannot be done on the same set of data. You have to have two different data. One data on which you run factor analysis, and you need another set of data to validate the model. Or at least divide, if you have large data, divide the data into two parts and run factor analysis on the first part. And these days, many people use in health sciences, many people use NFHS data. It's a very large set of data. Divide the data into two parts and run factor analysis on one and confirmatory factor analysis on the other. Then you will get good results. I hope similarly, the question of chi-square as a test of goodness of fit. What is chi-square? And I was telling you about my own struggle, and that it took me a lot of time to understand how the S minus sigma can follow a chi-square distribution, while S and sigma are matrices. So it refers to actually some books forget to write, or they take it to be granted that this is taken to be granted that S minus sigma means the determinant of that. So friends, these are some issues I have posed before you. I hope now conceptually you are more clear about SEM and you will use SEM more carefully, and it's possible that after applying SEM you regret you are not getting good results. No problem. This is part of the research job. Do not think that these advanced techniques will provide always fruitful results as simple univariate techniques of mean, mode, median, skewness, or kurtosis produce. So thank you very much.